Hello, this is Dr. Hanaa Assil, and this is about naming organic compounds and isomerism, types of isomers. So let's review quickly how to name organic compounds. We know that in order to name an organic compound, we determine the longest chain of carbons containing functional group. So if it has one carbon, its name should start with meth, 2 carbons eth, 3 carbons prop, 4 carbons but, 5 carbons pent, and 6 carbons hex. And then we look at the branches. We include the branches and we start counting from the side that is nearest to the functional group. So what functional group do we have? If everything has single bonds between the carbons, then it's an alkane. So the name would be methane, ethane, propane, and so on. If it has a double bond somewhere, it's an alkene, ethene, propene, butene. If it has an OH, it's an alcohol ending with ol, ethanol, propanol. If it has C double bond OH, it's an acid ending with O weak acid. So methanoic acid, ethanoic acid. And then we look at the substituents or the branches. If it has just one carbon, it's a methyl something, 2 carbons and ethyl something. And if it has some other substituent like chlorine or bromine or iodine and so on, then it could be a chloro something, bromo, iodo, amino, nitro, and so on. So let's just remind ourselves, how do we name this? We said it has how many carbons? 4. We said 4 carbons, the name must start with but. And then it has which functional group? Well, it only has single bonds between the carbons, so it's an alkane, so that is butane. What about this one? 2 carbons. We said 2 carbons, the name should start with S. It has a double bond, so it's an alkene, so this is ethene. 1 carbon, the name should start with meth, and it has an OH, alcohol, so that is methanol. What about this one? 2 carbons, eth, and it has that group C double bond OH, so it is ethanoic acid. Do we understand? So how do we name this compound? We said, first of all, choose the longest chain. That means the carbons one after the other. If you see this, can you see that I have this as the longest chain? So this is something that has 5 carbons, and we said 5 carbons is pent. Now, which functional group do we have? We have only single bonds between carbons. That means it's an alkane. That means it is pentane. Now, then we look at the substituents. Substituents are the groups that are not on that chain. So here I have 2. Each of them is a methyl group. We said CH3 is a methyl group. I have 2 of them, so it's a dimethyl. And then for each substituent, I need to put a number to indicate its position. Now we start numbering from the side that will give the lower number for the substituent. So these 2 methyl groups, one of them is on carbon number 2 and the other is on carbon number 3. So this is 2,3-dimethyl pentane. What about naming this compound? Well, let's again choose the longest chain. Where is the longest chain? This is the longest chain. It has a total of what? 6 carbons. So that means it is hex. Now, where are the substituents? We said we count from the side that gives the lower number for the substituents. So I have 3 CH3s, that means 3 methyl groups, and that means I have a trimethyl hexane, and I need to give a number for each methyl group. I have a methyl group on carbon number 2, another one on carbon number 2, and a third one on carbon number 4. Again, we number from the side that gives the lower number. So we know that there are different types of formula. We could be required to draw displayed formula, and this shows all the atoms and all the bonds. So for example, if I'm trying to draw displayed formula for ethanol, we said S means 2 carbons, all means it has an OH. So this is the displayed formula showing all the bonds. But if we're required to draw structural formula, then we just collect all the hydrogens for each carbon. So the first carbon on the left has 3 hydrogens, then the carbon on the right has 2 hydrogens and 1 OH. So this is structural formula. Of course, we know the molecular formula is just counting all the carbons, all the hydrogens, and all the oxygen. But we also have something called skeletal formula. Now, what is the skeletal formula? You should realize that if I want to draw, for example, the structure of propane 1-ol. In propane 1-ol, I have 3 carbons and I have an OH. If we look at the carbon skeleton, so where is the carbons in the structure? We have 3 carbons and an OH, and you should remember it is understood that each carbon must have a total of 4 bonds. So if I draw it like this, each carbon is on the end of a line. So a line in the skeletal formula indicates a bond between 2 carbons. So this is the skeletal formula for propane 1-ol. Let's try to draw for propene. Again, 3 carbons, but now I have a double bond. Again, this is the carbon skeleton of the structure, so I can draw it like this. Propanoic acid means it has a double bond OOH somewhere, total of 3 carbons. That means this is the carbon skeleton and this is the skeletal form. Okay, so that means if I want to draw butane, I can either draw displayed formula of butane or structural formula or skeletal formula. So if we say give the systematic name for this, now this is the skeletal formula and it's understood that at the end of each of these lines there is a carbon with the required number of hydrogens. So again, how do we name it? We look at the longest chain. The longest chain is this, made up of a total of 6 carbons, and that means it should be something hexane. And then we look at the substituents. We said at the end of each of these lines there is a carbon with its required number of hydrogens. That means we have a methyl group at the end of each of these lines, and that means I have 2 methyl groups, so it is a dimethyl hexane. Now I need to specify each methyl is on which carbon. So if we say we count from the side that gives the lower numbers, that's why we counted starting from the left. So I have a methyl group at carbon number 2 and I have another one at carbon number 4. So this is called 2,4-dimethyl hexane. Now let's apply all of this to drawing isomers. You should remember isomers are 2 or more compounds having the same molecular formula but different displayed formula. So we said there are different types of isomers. So I could have chain isomers in which I am changing something in the chain. For example, what is the name of this compound? This is propane 1-ol, propane 2-ol. Both of them have the same number of carbons, same number of hydrogens, same number of oxygens, but the only difference is the position of the OH. One's on one end, So that's propane 1-ol and one's in the middle. And remember, how do we draw skeletal formulas for this? These are the skeletal formulas. Please make sure you are acquainted with all of this. What about drawing isomers of butene? Well, but we know has 4 carbons and ene means there is a double bond. Now, where am I going to put the double bond? That's the difference. So once the double bond on one end, either on the left or on the right, that's the same compound, because in either way it is but1-ene, or the double bond in the middle, so that is but2-ene. Again, how do we draw skeletal formulas for this? Please note that these would be the skeletal structures or skeletal formula for these isomers. What about isomers of butane? Butane is something that has 4 carbons. So either all the 4 carbons are after each other, or 3 carbons in a chain and the 4th is a branch. So these are the isomers of butane. Pentane. How do we draw isomers of pentane? Again, either all 5 carbons, one after the other, or 4 carbons in a chain and one of them is a branch, or 3 carbons in a chain and 2 of them are branches. So if we say which structures represent a pair of isomers, we are looking at 2 of them having the same number of carbons. So if you count the number of carbons for each of these pairs, you will find that this one has how many carbons? 6 carbons. Both of them have 6 carbons, and the only difference is how these carbons are arranged. So these are isomers. The others do not have the same number of carbons. Another type of isomer is geometrical isomers. And these are isomers when we have a double bond. So if we have a double bond and each carbon of the double bond is bonded to 2 different groups. So if I have a double bond, 1 carbon on the left is bonded to a hydrogen and CH3, so these are different. The other carbon also is bonded to different groups. Then what I have is geometrical isomers, and this is because the double bond has what we call restricted rotation around the double bond. That means if the CH3 is up, I cannot rotate it and bring it down. It is fixed, whether the CH3 and the H's are up and down in a certain position. You cannot turn it around. Remember that single bonds can rotate around each other. So if I have a single bond, I can rotate that. If we say that red ball represents oxygen, I can rotate it around the single bond and bring it down. So whether it's up or down does not make a difference. But if I have a double bond, there is restricted rotation about the double bond, and that means each of these substituents are fixed. You cannot rotate it and bring it down. And that means we have 2 options. Either the similar groups on both carbons are on the same side of the double bond, so we're going to call that a cis isomer or a Z isomer, or the similar groups are on opposite sides of the double bond. That is called trans or E. So, for example, if I have this compound, the carbon on the left is bonded to a hydrogen and CH3. The carbon on the right is also bonded to a hydrogen and CH3. Now, where are the... First of all, we look at which one has the higher MR. Of course, if I'm comparing H to C, C has a higher MR. Now, the ones with the higher MR on both sides are on the same side of the double bond or on opposite sides of the double bond. If they're on the same side, that's called the cis or a Z. If they're on opposite sides, that's called a trans or an E. Remember that when we draw a skeletal structure for these, the cis looks like this, while the trans will look like this. So if we say determine which is E and which is Z, well, for each carbon, we're going to choose which one has higher MR. So the carbon on the left, if we're looking at the structure on the left, the carbon on the left of the double bond has a CH3 and a C2H5. Which one has higher MR? Of course, one carbon or two carbons attached to each other, then it is the two carbons. So we look at the one with the higher MR. So the C2H5 on that side is higher MR. Now if we look on the other side, which one has higher MR? Well, comparing chlorine to carbon, remember we are comparing the atom that is immediately bonded to the carbon. And if they are the same, then we look at the next atom that is bonded and so on. So we're comparing here chlorine to carbon, not the OOH. Chlorine to carbon, chlorine is the one with the higher MR. So if they are on opposite sides of the double bond, then that one is the E or the trans. The other one has the two groups that have higher MR on the same side of the double bond, then this is a Z or a cis. What about this one? On the left, we're comparing which one has higher MR, bromine or iodine. And we know that iodine has higher MR. Now, on the other side, fluorine and chlorine, well, chlorine has higher MR. So that molecule on the left has the groups that have higher MR. On the same side of the double bond, it's a Z. The other one has them on opposite sides of the double bond, that's an E. What about this one? Again, comparing bromine to fluorine, well, bromine is higher. Hydrogen to chlorine, chlorine is higher. So when they are, the one with the higher MR, on the same side of the double bond, again, that is a Z. If they're on opposite sides of the double bond, that is an E. So which compound has EZ isomers? Remember, we said in order to have an EZ isomer in the first place, we must have the carbons on both sides of the double bond. Each of them should be bonded to different groups. So if I draw but1ene, this is but1ene. Now where is the double bond? Where are the carbons on the sides of the double bond? Well, this carbon is bonded to the same group. That means this compound cannot form cis-trans or EZ isomers. What about but2ene? Each carbon is bonded to two different groups. Yes, this can form an E or a Z. What about 1,1-dichloroethene? Again, that carbon is bonded to similar groups. It cannot form EZ. 2-methyl but2ene. Again, that carbon is bonded to similar groups. Remember, carbon of the double bond bonded to similar groups cannot have a cis or trans or an EZ isomer. Again, if we're required to say what is the systematic name for this compound, again, remember we said we're going to choose the longest chain. This is the longest chain. And then we're going to start numbering from the side that is nearer to the functional group. So the functional group here is the double bond. So I need to start numbering from the side that will give the lower number for the group. So this is 6 carbons. It's a hex. And it's a hex 2-ene. Now I have a substituent here, a methyl group here. And that is on carbon number 5. So this is 5-methyl hex 2-ene. Now, is this an E or a Z? Well, if we look at it, remember that each carbon must have a total of 4 bonds. If you cannot see 4 bonds, that means there are hydrogens. So this is the structure actually, and that means the hydrogens are on opposite sides of the double bond and the carbons are opposite sides. So this is an E5-methyl hex 2. Which molecule has a geometric isomer? Again, we said to have a geometric isomer, we must have first of all a double bond. Then each carbon bonded to the double bonds must be bonded to different groups. So let's look at A. That carbon is bonded to same methyl groups. In B, do we have double bond? Yes, and that carbon is bonded to the same groups, so no geometric isomers. Each of the carbons is bonded to the same group. This one, the carbons are bonded to different groups, so this is the one that will have a geometric isomer. Okay, we're going to stop here, and thank you for listening, and I hope this was useful to you.